there was a choice. All right, never mind. I can start now if you like.
Okay.
All
So,
right, so
dear
I'm
friends,
sharing.
so today we start a series of seminars devoted to application knot in physics. And the first talk will be done by Luke Kauffman, and you can see slides. The title of the talk is Physical Knots. So, Luke, please start.
Thank you. Title of this talk is Physical Knots, and I'm since it's introducing our conference, I thought I would make it a kind of general talk, and also it will include certain specific things that I'm working on. But I'm going to make it a short general talk about knot theory, and then it will go into specifics about some things about knotted vortices. So here's a puzzle that I like to give. Is this knotted? And you might examine this and maybe jot it down. And a little later, if we still have time at the end of the talk, I will let you know what the answer to this question is. But this underlines the perennial and fundamental problem about knot theory, which is that one can take a representation of a curve in space, and it will not be easy to tell from the representation of the curve in space whether or not it's equivalent isotopic, ambient isotopic to an unknot or not, or to another such curve. And so comes the problem of this subject. As I said, I'm going through some points about knots. So here's another point that I like. Knot theory is related to knotting, which goes back for thousands of years. And here is a book on Celtic knotting that was shown to me by David Evans a long time ago. It was published in 1900 by Romilly Allen. And in his book, he pointed out that one way to design Celtic knot patterns, such as the patterns you see in the left-hand side on the cover of the book, is to start with a regular pattern and then to take some of the crossings and remove them, replacing them by what we call smoothings. I don't know what Celtic knot tires called them in those days, but I'll call them smoothings, re-smoothing the crossing one way or another to produce patterns of this kind. And if you were to look, for example, at some of the patterns, the rectangular ones over on the left, you can see that that's exactly how they're made from a regular pattern. And what was ironic about this was David Evans showed me this, and this diagram is exactly like the kind of diagram that we might draw since the middle 80s in calculating the bracket polynomial invariant. But of course, there was no polynomial invariant for the Celtic knot tires. But to this day, if you go to websites about Celtic knot tying, you will find even small programs that allow you to do this kind of re-smoothing, made with people who are not thinking about the theory of knots as we do. 83 years later than Romilly Allen's book, your lecturer wrote down this equation, not having read Romilly Allen, and this began with the help of previously discovered Jones polynomial, a long story of developing relationships among topology, combinatorics, statistical mechanics, quantum theory, and more. We won't enter into this part of the story in this talk exactly, but a hint or two is worthwhile. So calculations of this kind, expanding by smoothing one way or the other, can lead, after adjusting the coefficients correctly, to the detection of knots from their mirror images in many cases, and many other questions about knot theory interrelated with this kind of calculation and related kinds of calculations. For example, if you apply that Celtic idea to a given knot like the trefoil knot, you arrive at 8 this case, and in general 2 to the n smoothing patterns, depending on which way you smooth each crossing. And they can be thought of as the states of a related physical system to the knot, or related to states of a physical system. And this went on for some time, and around 1998, Kovanov viewed these states as a category. That is to say, he put an arrow in there, and the arrow is going from one type of smoothing to the other type, which I had discriminated as A and B before for you, but not bothered to define. And you will then have a cube of states, starting with the vertex of the cube at the top and going down to the vertex of the cube at the bottom, where all the states are smoothed in the B way. And then, to make a long story short, Kovanov asks, well, here's this category which you could associate to a knot diagram. How can you obtain topological information from a category? And if you're thinking in that level of abstraction, you could think about, well, categories have cohomology theories associated with them. Perhaps you could do something with that, and he did. And this led to a whole raft of new invariants called linked cohomologies. So that's a very quick talk about some of the developments in the knot theory. But let's also talk about some actual properties of knots, physical and magical in this case. Here's another question. What about this? Is this knotted? I assure you it is. And I've made a square knot here with a little loop at the bottom. And now I'm threading it a little further. That's the knot you just saw. That, I assure you, is knotted. And it doesn't seem that this is doing anything but making it more complicated. And yet, as you will see, the resulting configuration was, in fact, unknotted. And in fact, it's quite interesting physically to think about such evolutions. What will unknot a knot? Could you be sure you could unknot a knot by putting some force on it and pulling it like that? Not easy to analyze. Here's a variation of this where I have a ring on the rope. From here on, I'm doing the same thing I did before. I have threaded the ring in such a way that there is no linking number between the ring and the rest of the rope, but that doesn't guarantee that it will come off. The rest of the rope is going to be unknotted because it's threaded just as it was before. And what will happen to the ring in relation to that unknot is a little bit of suspense at the moment, but perhaps you see that, in fact, it's going to come off. So experiments like this are good for thinking about knots physically, and they're also good for performing some kinds of close-up magic like that. What's the least sort of mathematics you need in order to prove that a knot is knotted? Here's an example of it. I'm going to color the arcs of this knot diagram with colors, and the colors could be called A, B, and C, or they could be called red, blue, and green, or they could be called dark, medium, and light with those shadings that you see there. And I'm going to follow a rule that is that either you will see 3 colors at the crossing, or you will see only 1 color at the crossing. And this follows the rule here. This is allowing 3 colors at every crossing. And then we're going to see what happens to this knot as I move it around. And to see if I do what I haven't yet introduced, the Reidemeister 2 move, if I do a little slip under move, and then I have one color meeting another, and the new arc can be colored by the third. And this can go on for a while, but then near the bottom of the slide, you see a single color approaching a single color. And that single color, when it moves under it, is allowed to still be a single color. So we're getting a unique way to recolor the knot. And what you see in the last movement is a switch across a triangle, and that's called the third Reidemeister move, that little bit of isotopy that the knot underwent. If you watch from one picture to the next, you see that a triangle on the right became a triangle on the left, and that a color that went to 3 and then to 1 became a color that went from 1 and then to 3, and everything was peaceable. There was no conflict, and we recolored to the bottom diagram. And this always works if you check the cases, so that if you start with a 3-colored knot like the trefoil was, and look at any knot that can be obtained from it by moving in this fashion, then it will also be 3-colored. But the unknot is 1-colored, and there's no way to get from 1 color except to 1 color, and so there is no diagrammatic way to relate the trefoil diagram to the unknot, and we have proved that the trefoil knot is knotted. That is the form of this, and the form of this becomes algebraic in the way that is happening in this diagram. You can think of A and B as being the colors, so that AB is equal to C, and read that all of these things were working out correctly. We get that if you have a color coming in to meeting itself in a little loop, then it should come out A applied to A, but that's the same as A. And if you have a color that is meeting B and then meeting B again, then you see you get A back. And what I mean by a color meeting a color is what I'm demonstrating here, that you ask what color could I put in the line beyond if I had an A and an A, and the answer was just A. So I have a rule that says that if A and A meet, then I get an A. If A and B meet a B, what can I get? Well, read it for C. A and B form C, and C and B meet, and there were only 3 colors in our system, and that would have to be A again. C and A combined to give you B. C and B combined to give you A. But in general, you can think of an algebraic rule that would encompass this for some more general system than the 3-coloring system. And this is showing you what would have to happen. You see that the AB would meet a B, and that would be AB meeting B again, but it should be A, so you should have AB, B equals A. And similarly for the Reidemeister third move here, A would become AB, which would meet C, which would give you ABC. But if the line was shifted down below, A would meet C to give you AC, and then that would meet BC, and so you would have AC meeting BC, and you would need a distributive law in the algebra. So you get an algebraic system called the quandle, which if these axioms are satisfied by a certain algebra, then it can be used to label knots and then distinguish them as a result. And so this is what algebraic approaches to studying knots look like. As I said, you have the 3 moves. That goes back to Reidemeister's book, Knot Theory, published around 1931, I believe. And prior to that, the work of Alexander, J.W. Alexander, and Briggs, who proved in the 1920s that these 3 moves are sufficient for doing topological equivalence of knots and links. And in fact, it's quite remarkable that these 3 moves were employed but not fully theorized about by Maxwell, by Clerk Maxwell, who studied knots in the 19th century. He and Tate and others studied knots, and Maxwell had these moves. But Alexander and Briggs actually proved that two knots embedded in three-dimensional space, um, if you watch their shadows down in a projection plane, if there is a movement from one knot to another that's isotopic, taking one to the other, then the shadows can be arranged so that they move little by little from one diagram of the knot to another diagram of the knot by these moves. And so these moves become a graphical reformulation of the theory. And from there, you might think the theory would then be just solved. You understand what the equivalence classes of these graphs are. But in fact, it's a wonderfully difficult problem which has lots of partial work on it to this day. And all of this is going on in a species of graph theory called knot diagrams, like the ones on this page. And knot diagrams even occur as the end points of certain physical investigations. For example, this photograph of DNA over here, this electron micrograph of DNA, due to the work of Stasiak, Spengler, and Cosarelli in the 1980s, was a sufficiently clear picture of DNA as a knot diagram to pinpoint that the DNA is knotted. And the techniques that lead to the picture are quite difficult. It's not just a matter of taking a snapshot. The DNA had to be coated with protein in the right way and other techniques, electron microscope techniques, in order to obtain pictures that were reliable. So knot diagrams get around in this way. I'm making a further remark about the Borromean rings here. If you weren't going into the details of theory about knots, you could nevertheless appreciate the following fact about the Borromean rings. They're linked. You can't unlink them. Try it, make one. On the other hand, they have a scissors, paper, stone kind of property. That is to say, if you look at this picture, you see that red surrounds blue, blue surrounds green, but green surrounds red. So it goes around in a cycle like that. And some proofs that the Borromean rings are linked actually use that idea, but we won't go into it. I already said a few remarks about this bit of physical knotting. You might ask yourself, looking more closely at the picture, are you sure about all the crossings in this picture? I think actually, if you look at very carefully, you can see that you can make the decision and then ask yourself, on what basis did I make the decision? Because it isn't perfect information you have here, but it's good enough. And there are many electron micrographs of knotted DNA, some clearer, some not so clear. It'll give you a hint about where it ought to be on the knot tables. I claim that on the knot tables it looks most like 6-2, and you could verify that it is 6-2 there in the knot tables. And this is the knot tables in modern form. Knot tables were begun in the 19th century in relation to the work of Kelvin, Sir William Thomson, who had a theory that knots corresponded to knotted vortices in the luminiferous ether. So he thought that fundamental physics was related to knots, understand the idea of atoms. And he commissioned Tate and Kirkwood and Little and got them to make knot tables. And this is the inheritance of that knot tables in a modern form, computer drawn. And as I said, I wanted to do a little surveying of knots from theory to physical in this talk. So I have little vignettes, some of which will expand out into some more actualities. But this is only one slide about the whole subject of DNA knotting and recombination. recombination here is what you see diagrammatically. Two arcs come near one another and end up being replaced by a crossover. And in this picture, they're always being replaced by a kind of right-handed crossover. First in K1 once, then once again in K2, then once again in K3, and once again in K4. And if you are up here in the world of the knot diagrams, you can examine what such a recursive action on knot diagrams would do. It will give you a spectrum of knots and links. K1 is a hop link, K2 is a figure-8 knot, K3 is a certain link, K4 is another knot. And you could then look at a corresponding experiment devised to do processive recombination in DNA using the electron micrograph technique and find that you would see in the spectrum of electron micrographs the same knots if you did, which did happen in certain cases, does happen in certain cases, then you know something more than you could have known. For to tell which way the recombination happened would not be easy, but to tell what global knot you got would be much easier. And so if they all came out in this spectrum, you would be pretty well assured that the recombination pattern was indeed the addition of that single right-handed twist, because you can, up in the knot theory end of things, see that a quite different topological spectrum would happen if it had been a left-handed twist or a double twist or other kinds of things. And this gives rise to both problems for knot theory in the sense of what happens under iterated processes to knots and the relationship with the physical world. Those are just some slides about the DNA. So nature doesn't ignore the topological problems that occur. It solves them, in this case, with enzymes that can do things like cutting a bit of DNA apart, allowing the DNA to slip through and come back, and other forms of recombination. Now we get to something else, physical nonetheless. Here is a printed knot that I made in the course of work with Daniel Sandin. And we've been having a little project to investigate the turning of the normal vector to the curve, which you can find if you have a curve. You just have a sequence of points. It's a discrete curve. It may be given to you by your file for the drawing of that curve, or by the mathematics of getting the curve, and you can plot that curve. You can plot it in programs like Rob Shirine's Knot Plot, or ones that you brew yourself. But given that you have such a sequence of points, you can find at each point a normal and a binormal. You can find a local for an A-frame. You can look at the, say, the binormal, call it the spur, and then watch how the binormal is twisting around the knot and plot it by using some local graphics, and then you can even make models of how that worked and print them. And this is a printing of a trefoil knot with the twisting that you see having to do with the way the binormal is turning. So you can go from mathematics to the physical in this way. As I was saying before, Lord Kelvin hoped to go from back and forth between the mathematics and the physical. He hoped to understand that atoms are knotted vortices in the luminiferous ether. He hoped. But it wasn't until many years later, maybe I have the slide for that. Yes, but people at his time did speculate about knotted vortices, and even philosophically. This is a drawing by Leadbetter of the vortex atom that the visionaries Besant and Leadbetter had hoped or did claim to see in their mind's eye as the beginning of the materialization of the spiritual into the actual. That was their viewpoint. And this part of the world of knots in relation to physics went on in the 19th century. And you might wonder, well, what happened then? And if you look it up in the Wikipedia under history of knot theory, you may find some opinions that you would agree or disagree with. You'll see here, the wiki says in 1867, after observing Peter Tate's experiments involving smoke rings, Thomson came to the idea that atoms were knots in the ether and chemical elements would correspond to links, and there would be vortex rings. And there was this rich idea that they started following. And the idea was also related to the beginnings of conjectures about knots. And Maxwell thought about this, and Gauss had an integral that expressed linking, and that's certainly related to electromagnetic theory. And this is the modern wiki, and it goes on correctly about that history. And then it says, curiously, when the luminiferous ether was not detected in the Michelson-Morley experiment, vortex theory became completely obsolete, and knot theory ceased to be of great scientific interest. It needs to be revised, this part of the wiki. But knotted vortices were not seen physically until very recently. Around 2012, Kleckner and Irvine. Kleckner was a graduate student of William Irivine at that time in Chicago. They found that they could produce knotted vortices in water and photograph them. And the idea is the same as the idea of producing a smoke ring. You can produce a smoke ring from a circular band in the shape of foil like this, so that as the water or the air goes past it, it will vortex and form a ring vortex. And you could either blow smoke through such a ring to form the ring vortex, or you could move the ring downward through water, for example, and the result will be a vortex ring emanating upward, not knotted. But then they said they took this idea seriously and tried to use knotted bands as the generators of vortices, and used 3D printing in order to create those knotted bands and tinker with them. And they were able to produce knotted vortices, knotted ring vortices in the water. So here's an unknotted vortex being produced by their method. You'll notice I'll run it again just for the sake of being able to see it. The band went down, and that was actual. It went down and the vortex flies up, and high-speed photography in their lab allows us to see the result. Here's the knotted one, and the high-speed photography allows us to see this very evanescent knotted vortex. So if the wiki had known about this, I think it couldn't have dismissed the whole subject so lightly. Let's look at that one more time. Oh, not that, that, there. These knotted vortices are indeed highly evanescent. They quickly disintegrate, and they disintegrate by vortex reconnection, like this in this sequence of pictures. Two parts of the vortex come near one another, and they interact, and they recombine. So there again is that theme from the same as with Romilly Allen's book on Celtic knotting that we mentioned a few minutes ago. The two lines might be near one another, and they could get re-smoothed into the other form. And that's the form of this, although the actual interaction is quite complex. And so reconnection of that kind tends to happen at various sites in the knotted vortex, and and take it by that kind of disintegration into a collection of unknotted, unlinked loops. And one could ask, how many reconnections do you need in order to do such a thing? So there have been many papers about reconnection, and this was one that we worked on. And in this paper, the model in back of this is not the knotted vortices in water, but artificial vortices produced by nonlinear Schrodinger equation and the evolution of that. And then you can make evolutions that happen in that computer mathematical space where the reconnection happens. So I'll do that one more time. Here's a trefoil undergoing, and in this film, it's quite simultaneous reconnection in those 3 points, and it turns into 3 unknotted loops, one unknotted loop, excuse me. Here's a more complicated version. I'm going to start with this knot and let it undergo some reconnections. And as you see, it started with 6-2. Then it turned into a link. Then it turned into a trefoil knot. Then it turned from the trefoil knot, it turned into a hop link, and then it turned into the unknot. And we underwent 4 reconnections in order to do it. What did it actually look like? Oh, excuse me. I will come back to this slide and this one, and this one, and this one. Sorry. I wanted to, oh, maybe I didn't plan my slideshow quite the way I had in mind. I wanted a slide. Well, we'll just let that run. I had a slide which I forgot to put in here, which shows you how, starting with 6-2, you can see exactly how the reconnections happened that get you from one to the next to the next. And I have missed that slide, so you have a nice puzzle. You can start with a diagram of 6-2 and find that if you do a reconnection in the right place, you will end up with a link. And then if you do a reconnection on that link in the right place, you'll end up with a trefoil knot. And let's just discuss trefoil to hop link for a moment. If you started with the trefoil knot and you did a reconnection right there, you would end up with a hop link. You would end up with a little link there and another one here. And that's the best you can do by the time you're down to a trefoil, it would seem, if you try strategy on it. In order to get from the trefoil down to the unknot, you seem to need to go through an intermediate hop link and then down to the trefoil knot, down to the unknot. You won't be able to do it in less than 2 steps. So it seemed to take 4 steps. Does it necessarily? So now I want to talk about an abstract framework for this. And the abstract framework looks like this. You begin with 2 bits of curve that are oppositely oriented to one another in my diagrams, but oppositely oriented also means the vortices going around those lines are turning in the right way. Use the right-hand rule to produce a little vortex circle around the line, and then you will see that it rotates in a certain way in relation to the arrow. And if it rotates in that same right-hand rule way according to an arrow going in the opposite direction, that is the correct interaction for the vortices so that they can recombine. So it's an oriented matter where the orientation on the line refers to the rotating direction of the vortex. And then you can go through the resmoothing, and you will go through a surface in 4 space. So I wish to visualize the surface in 4 space that happens when a reconnection occurs. And it could go through a saddle like that. The other part that a mathematician likes to do doesn't quite happen in physical reality, but we can imagine it mathematically. We can say if we have an isolated circle that's unknotted, why then we'll allow it to die, time going up the page. You see a death there. Or you could allow a circle to be born. So for mathematical purposes, we often allow circles to be born or die. And then we can think of evolutions in the mathematical space that go from one circle to another that trace out of some genus in the interim. So in the bottom of the slide, I have some examples. Here is a simple genus zero cylinder. Nothing happened. It just is in time going along, and ending up where it ended up. In the other one, if time goes up the page, then what happened was that a circle got born, and then it underwent a reconnection with the other circle and became one circle, and that's at the top. Or if you went from top to bottom, a circle, it underwent a reconnection, and then one circle died and the other one survived. But other things can happen. You could give birth, as on the right, you could give birth to two circles, and then those two circles could go through a saddle point and die. Here is an example of such a sequence for the trefoil knot. And here I've shown exactly where I did my work. Let me allow myself a pointer by going out of the slideshow for a moment. Here's the trefoil knot, and I'm going to have a reconnection happen right there, and then that will turn into this. And now I have a hop link, so I've gone, time is going down the page for me. And so I've gone from one curve to two. And now I'm going to go through another one between these two curves, and I'm going to have it happen right here, melding those two curves back to one curve. And those two saddles together take me through a topology of surface in force space that I can see did happen. And that topology of surface is a torus with two holes punctured in it. So I have a genus 1 surface between these two. And the question of how many reconnections and what sort of reconnections will allow one knot to go to another, in this case, a trefoil to an unknot, is tied up with the question, what kind of genus of surface could happen between one curve and another curve? And if you could get a concordance, which is what we call that surface in between, of genus 0, then there would have been no saddle points, perhaps, or we could count how few there were, and then we would know that the number of reconnections was very small. So we can estimate it that way. Let me go back to my better viewing. So here is 6-2. Oh, I did have it illustrated here. I forgot just how I had done it. So here's 6-2. And again, let's get a pointer. So here's 6-2. And I'm going to decide to do a reconnection right there. All right. Notice that with in the diagrammatic world, the reconnection takes you from oppositely oriented nearby curves to oppositely oriented nearby curves. And okay, but now I have a link with these 4 crossings between the 2 components. That's the link you saw in the picture. And now I'm going to undergo another reconnection that takes me to a trefoil knot, and that's between these 2 right here. And that's what happened if you look at the movie of what happened mathematically in that Gross-Piatowski evolution. You get to a trefoil knot, and then from the trefoil knot, you get down to the unknot by 2 more reconnections in the form that we just discussed. And that's what happened in the physical simulation. Is that the least thing that you could possibly have, or is there something better? let's find out by going back to the slideshow and looking at the next slide. The fact of the matter is that mathematically you can switch a crossing with 2 reconnections. Isn't that interesting, right? That's a mathematician's observation about the cobordisms and concordances that's fundamental to the subject as mathematical subject. How do you do it? Well, it may not happen so easily physically. I do it in the following way. I put in a little twist that can happen up to isotopy. Now I have 2 oppositely oriented edges there, and I go through a saddle, and now I have a little line which is passing under another line. So up to isotopy, I can slip it out and then push it back over the top. And then I can go back through a saddle and get the crossing switched, and I can remove that little curl if I want to. And I'm back to where I started, 2 lines crossing, but now they're switched. And that will trace out a bit of surface, a bit of torus, 2 reconnections. Now, you could ask, will that happen physically? Under some circumstances, will something like that happen physically? It doesn't look like it would happen so easily in a physical evolution. William Irivine and I have been meaning to do some more experiments with nonlinear Schrodinger evolutions to see whether maybe such a thing could happen in them. But in the evolution, quasi-physical as it was, this is not what happened, and it required 4. But here is the ideal world. Here's the ideal world for you. Here's 6-2, and in this ideal world, 2 recombinations took you to switching the middle crossing in the 6-2. So my question is there a physical context in which that might happen through this kind of flow? But if it did, you're unknotted. That knot unknots by switching that 1 crossing. And if you stare at it a little bit, you see that indeed the knot right there in the middle next to the unknotted curve, it's unknotted, it just comes apart. And so that means that the mathematical reconnection number for the 6-2 could not be more than 2. And we would like to show that the mathematical number, in fact, is equal to 2. So now we're edging from the physical question into a mathematical question. We've seen that a physical sequence of reconnections takes 6-2 to the unknot in 4 steps, but in principle, this can be done in 2 steps. We expect this sort of difference between physical pathways of reconnection and available topological pathways, and we're investigating that. Here is some formulation of it. We want to get lower bounds. So we'll let R of K be the least number of reconnections needed to transform the knot K to a collection of unlinked circles. And that means least number in any way you manage it by pushing the knot around topologically and getting oppositely oriented arcs near one another and going through. There's a classical invariant of knots called the signature of knots. And it calculates to be -2 for the trefoil and -2 also for 6-2. And one has that the absolute value of the signature of the knot is less than or equal to the reconnection number. And the proof of it goes as follows. You can think of the genus of the surface you generate, and you can show that twice the genus that you generate, which I've called the 4 genus, is less than or equal to the reconnection number. That's what I was indicating with my pictures. And then a theorem from classical knot theory due to Murasugi that the absolute value of the signature is less than or equal to twice that genus. And so therefore the absolute value of the signature is less than or equal to the reconnection number. And there are other variations of this kind of result that give you lower bounds on reconnection number. In this case, absolute signature was 2, and so we couldn't get less than 2, and we know that the trefoil requires 2 reconnections no matter how you do it, and so does 6-2. What does signature look like if you're going into knot theory? Then there are additional apparatus, some of which are quite geometrical that get you there. there exist surfaces whose boundary is a given knot. I've indicated here a surface whose boundary is a certain knot, and it turns out it's the trefoil knot. And on a surface, there are canonical curves that form a basis for the first homology. And you can look at linking numbers of those curves, even though they intersect, by pushing one into the complement of the surface, push it along a normal. So if you pushed A along a normal there, you see you would get a linking between A and B. And if you pushed B along a normal, you would get no linking between A and B. And there's a notion of self-linking, which I won't worry you about, and you get a matrix of linking and self-linking numbers called theta, due to Seifert in the 1930s originally. And by symmetrizing the Seifert pairing, by taking theta plus theta transpose and taking the matrix signature of that, you get the signature of the knot. And it is that signature of a matrix that Murasugi proved was a lower bound to genus in the four-ball. There's lots of beautiful questions about what kind of genus and what kind of surfaces in the four-ball knots can bound. Not all leak reconnections, of course, lead to the production of genus. For example, this slice knot below, one reconnection is needed to undo it, and no genus is produced here. Now I'm going to show you a beautiful experiment by Alexyenko, which he did in 2016. Professor Alexyenko is in Novosibirsk, and his work was introduced to me by Renzo Rica a few years ago. And what he shows is a moving vortex that undergoes a reconnection, just like this cartoon I've drawn. It does slide under itself. I was asking before, might it slide under itself in orchestrating a switch? Well, it comes close here. The vortex slides under itself, and then it undergoes a reconnection right where you might think it did from this picture. That is between here and here, right? And it happens like this. Oh, you say you couldn't see it very well. Maybe you'd like to look at it again. Oh, you say you couldn't see it very well. Maybe we should slow it down. Here's some shots from that evolution. The forming of the little twist. The movement of the little twist underneath as it comes upward. The vortexing is happening in a cylindrical geometry that gets wider at the bottom than it is at the top of a turning vortex. So that has to do with the physicality of the loop rising. Loop has risen a little more. And now you can begin to see where it might vortex. And indeed, over there, it's beginning to look a little wiggly and getting close. And I wish the film had 100 frames from here to the next frame, but it has only one. So there's the reconnection without any interior detail. But having done the reconnection, there's the loop now linked with the main vortex line. So this is a case where actual linking can come from no linking at all. Very beautiful. And I've illustrated the cartoon again for you. So it's very possible that some of the imaginings of topologists would actually happen in physical reality here. Here's another film, and Renzo can remind me whether this is coming from Alexyenko's lab or another lab. I have unfortunately forgotten. In the last few minutes, I wanted to continue answering the wiki about the life and death of knots in physics. I've been fascinated by this paper, which was written in 1971. Ever since I met Herbert Yela, he must have been about 75 years old when I met him at a conference in Louisiana State University in the middle 70s. He was quite taken with the idea of Kelvin pushed down to the elementary particle level. He felt that elementary particles like quarks and baryons were knotted quantized flux. And he had many beautiful pictures of the knotted quantized flux loops and how they should behave and how particle interactions should be intermediated by their topological geometry. Of course, it was, well, I shouldn't say of course, but his work was not very analytical, and so didn't get caught into the mainstream. But there's Kelvin's idea again, happening in a physics paper. And we talked with him at that conference. He was very enthusiastic, and he carried a collection of rubber tubes with him that he could tie into the knots and show us how particles were interacting. But many years later, we have the following speculation. Protons are made of quarks. Quarks are bound by the gluon field. Glue balls are closed loops of gluon field. Can gluons be knotted? You see what I'm saying? Two quarks, if protons collide with protons, two quarks may fly apart. A quark and an antiquark may fly apart. And in between them is gluon field, which gets very strong as they fly apart. And produces a kind of tube of gluon field between them. And this winds around in space and perhaps gets knotted, this loop, this line or string of gluon field, and then the ends touch one another and form a closed loop. Such a closed loop of gluon field is called a glue ball. And the energies of glue balls are part of the measurement of spectra of results of proton-proton collisions. So people have asked the question, are glue balls knotted closed strings in the sense of string that I just told you? And perhaps one could find out about their energy levels in terms of knots and links. And perhaps such things are related to inflation at the beginning of the universe. So this is recent research speculation. But what is the idea here? For Keppert and Buini, it's a very concrete idea. They say maybe the glue balls are knotted, and maybe they have a tendency then to contract to least forms of the knot. But their energy would be constrained by the least form of the knot as the knot got pulled down into a tight form. And we can do computer experiments, knot theorists do computer experiments where they try to find the least tightened form of a knot. And that could be measured, at least empirically, through the computer by examining the length of rope needed and the diameter needed, and taking the ratio of the length of rope to the diameter, that being called the rope length, but it's actually the scale-free rope length. You take the length of the rope to the diameter, and you use the computer to get a least model, and you get a number. So each knot has some numbers associated with it, often just one, which represents its kind of geometrical energy level. And what Keppert and Buini discovered was that the geometric energy levels, the rope lengths, correspond statistically to the observed energies of glue balls from the scattering experiments. And that suggests deeper investigations which need be done or are being done. The demonstration you just saw is due to great Jason Cantarella, and you can find many demonstrations of this kind using his program at his website. Another example of knotting in physics is the knotted zeros in quantum states of hydrogen paper of Michael Berry, who pointed out that for the high energy states of a hydrogen atom, if you look at the places where the wave function is 0 in the time independent wave function for the hydrogen atom for high energy states, you will find phase lines, phase singularities, where the wave function is 0, and they're knotted. And this led off to a lot of research by a lot of people, and I won't make a list, of finding such phase singularity knots in quantum states and in electromagnetic states. So, so the point is that Kelvin's idea is alive and well, and interrelating with a lot of modern mathematical work. Sometimes strictly combinatorial work. I'll give you 2 examples and then we can quit. I like this example. This is very off the beaten track. Mr. Irivine wrote this paper for the Journal of Knot Theory and its Ramifications some years ago with his remarkable idea that you could think of particles that consist in 3 quarks as something like a Mobius band with different amounts of twist at its corners. So I've illustrated some different twists here. And so they're bound because they aren't quite really particles. They're the twists in the band. But they, as you walk along the band, you might find yourself going down and then up and then down. So this would be a down, up, down, and so on. And how will such things interact with one another? Well, they are going to interact by a cut and rejoin kind of operation. And then he finds, see, like that, a cut and rejoin operation. And then you will find that you may start with Irivine's neutron and let it undergo some kind of controlled isotopy, cut and rejoin, and find your some other switching rule which I don't understand, and find yourself with a proton, an electron, and an electron neutrino in the form of his classification of particles in terms of these twisted Mobius strips. That is, there are patterns about the interactions of particles which don't seem to require so much machinery. Another paper along the lines of not requiring a lot of machinery to see patterns in elementary particles is a paper by the category theorist Lambeck that I could show you. I didn't put it in the slideshow, in which he represents baryons and fermions by vectors in 4 space, just simple vectors. And the addition of the vectors corresponds to the interactions of the particles, and it works. So somewhere between some of the simplicities of the interactions and the topology, maybe some answers to questions about what's going on. Another example of this kind of combinatorial play is the work of Sundance, Bilson, Thompson, who catalogs representatives for particles, fermions, by framed 3 braids, and the framing consists of a sign on the 3 braid, as you see in these pictures. And the braids interact by braid multiplication, of course. And then, again, you will find that some particle can be seen as the interaction of 3 other particles by factoring the braid in an appropriate way. So his theory suggests that little bits of embedded surface could be thought of as particles, and they might be part of a larger surface network that are interacting. But what the controls and constraints, topological and otherwise, on these should be to make it into a real theory of particles competitive with the standard model, that's another question. And maybe it will happen in the future. I will end with as I began, with a trick. And this is a very famous trick that's related to Sundance, Bilson, Thompson's work. This trick is one that people out on the street making leather belts for you used. you have a belt with 2 slits in it, and you weave it. And you weave it in such a way to get what you want on the top part, and find that you can do this and then undo the bottom part, and there won't be any twisting left. You do it just right, and there won't be any twisting. The framing of the braid will disappear, and you get a bit of braiding on the belt with no twisting. And you can learn to do this quickly and make braided leather belts. The mathematical move behind this is to take a little trivalent framed vertex and twist it. You get some twists happening, and then you find that if you do the right number of them, the framing, the twisting will disappear, and you can obtain the braided leather belting by doing this sort of twisting. So this approach to elementary particle physics is just beginning, and we'll have to wait and see if elementary particles are braids, if knotted glue balls are real, and of course much more about vortices and their geometry and the relationship between knotted vortices and mathematical theories of cobordism and many other things in the course of this investigation into the future of knots and vortices and physical relationships between knots and the world. I'll stop there. I could go on with some more speculations like this one, but I'll stop.
Okay, thank you, Lou, and thanks to everybody for coming. And the next talk will be given next week by Marius Buliga from Bucharest, next Wednesday, June 10. So thank you. Thanks to everybody, and see you next week. Also, I will post the video of this talk on our YouTube channel and then email the link to everybody.
Thank you.
Thank you,
Thank you very
Lou.
much.
Thank you.
Okay, thank you.
Thank you very much. Yeah.